Thank you for joining us for Microsoft Research Summit 2021. I'm Danqi Chen, and I'm an assistant professor from Princeton University. Today, I would like to discuss one type of retrieval called phrase retrieval. This is a joint work with Jingya Li, Alex, Moonjin, and Jay Wu. Dense retrieval has become very successful in the past 1 or 2 years, and shown effective in question answering and many other knowledge-intensive NLP tasks. Different from sparse text retrieval methods, such as TF-IDF or BM25, which represent text as weighted backwards. These dense retrieval methods first map all the text units into a low-dimensional continuous space, and then we directly do nearest neighbor search in this space. This figure is from the DensePhrases retrieval paper, or DPR. So in this work, we show that DPR can outperform BM25 on popular question answering tasks, even with only using 1,000 training examples. And the table on the right here is from the recent KILT benchmark. It demonstrates that on a range of NLP tasks, including question answering, fact-checking, slot filling, entity linking, DPR can greatly outperform TF-IDF across the board. So far, most existing work focus on passage retrieval. For example, DPR chooses to use 100-word text blocks as the size of the passages. Some recent work shows that if you increase the passage length, using fixed length vectors can be not expressive enough to encode all the information and leads to a performance drop. In this talk, I'm going to talk about a paradigm called phrase retrieval, which can be thought of as the most fine-grained retrieval unit. Here, the definition of the phrase is basically any contiguous segment of text and are not necessarily linguistic phrases. So let's take a piece of text and a phrase in the text. In this example, we picked the police, which is the name of a band. And the goal here is to encode this phrase as a vector. So if we consider any segment text up to 20 words, there are basically roughly 60 billion phrases in English Wikipedia, and we need to encode and index all of them offline. Then for any question or input query, we also need to encode the question as a vector. Then we can just do the maximum inner product search in this dense phrase embedding space, and then we can retrieve the phrase with a maximum score. So it's very important to have in mind that all the phrases here are contextual. That means that there could be many vectors for the police, each with a different context. So you may wonder, why do we even want to solve this phrase retrieval problem? The answer is because phrase retrieval can be extremely fast at inference time. In this paradigm of popular retrieval reader models, we need to first retrieve the top 100 passages, and then apply a second stage reader model on top of the passages to get the final answer. And this second stage is always implemented as a BERT or T5 model with hundreds of millions of parameters, and they take a lot of time in practice use. If we can achieve phrase retrieval, that means that we can just throw out this second model and directly retrieve the final answer. This can give us great efficiency in practical use. So today I would like to introduce our project called DensePhrases and answer the following two questions. The first question is, can we even possibly learn dense repetitions for phrase retrieval at billion scale? And the second question is, if we can achieve accurate phrase retrieval, can we directly use it as a basic building block for all sorts of retrieval problems, including passage and document retrieval? I believe the answer to both questions are yes, and they have been answered in our ACL and MLP papers this year. So the idea of phrase retrieval was first pioneered by Minjun Xiu and others in their ACL 2019 paper. And at that time, they used a combination of the sparse and dense vectors. And this led to a very large storage and still greatly underperformed retrieval reader approaches. In our DensePhrases work, we completely removed all the sparse repetitions and directly learned the dense vectors for all the phrases. As a result, we made the storage 4 times smaller and the model 10 times faster. And the more important thing here is DensePhrases is also much more accurate and even matches the previous retrieval reader models. As you can see from the table below here, when we compare the dense phrases to DPR, we found that dense phrases can achieve similar accuracy and a similar storage, but it's 20 to 30 times faster on GPUs and can even run very fast on CPUs. So next, I'm going to give a quick sketch of how dense phrases work. Our goal here is to learn both a phrase encoder and a question encoder. And the first vector is represented as a concatenation of start and end vectors. And this design is very crucial because it means that at the inference time, we only need to store contextualized word vectors instead of the phrase vectors. And this can make the size at least 20 times smaller. And similarly, we also represent the question vector as two parts denoted by qstart and qn. By doing this, we can just compute the similarity between the question and the phrase as the sum of the qstart, hstart, and qn and hn. And to solve this very difficult learning problem, we also propose several key innovations. I don't have time to talk about all this in this talk, so please check our paper for more details. But the key ideas include: we propose to learn decomposable question and phrase encoders from the question answering datasets using question generation and knowledge distillation. We also propose to incorporate more negatives into the training process and present this idea called pre-batch negatives, which can effectively use representations from the previous mini batches. Finally, we also propose a procedure called query-side fine-tuning, which can allow only learning the question encoder without rebuilding this index. And we find this step very crucial because it can reduce the discrepancy between the training and the inference, and can also support transfer learning effectively. And we evaluate dense phrases on a comprehensive set of question answering datasets, and it achieves very competitive performance, although we only use 2 datasets to learn the phrase representations, and use all the other datasets for only transfer learning. We also directly consider using dense phrases as a knowledge basis, and ask it to output object entity for subject entity the relation query. In this example, the subject entity is the Beaver Creek, and the relation is country. We also find that dense phrases can perform very well on this slot filling task. So next, we ask the question: if we can do accurate phrase retrieval, can we use this as a basic building block for multi-granularity retrieval? The motivation here is very straightforward. Not all the NLP tasks actually require phrase retrieval. For example, for why question, why is the sky blue? We actually want the system to output a complete explanation sentence instead of a short phrase. So in our second paper, we build on a very simple intuition that since the phrase is actually the most fine-grained retrieval unit, if we can retrieve phrase, we can naturally retrieve the sentence, passage, or document that this phrase actually appears in, but the opposite direction doesn't hold. So with this view in mind, we can think of the passage representations as a set of the phrase representations in dense phrases. And the passage score can be just defined as a maximum of the phrase score in each single passage. And we conducted an apples-to-apples comparison between the dense phrases and the DPR for the passage retrieval. We actually find that the dense phrases already achieve better passage accuracy, even if the dense phrase is not trained for passage retrieval. And this improvement is especially pronounced for top 1 or top 5 accuracy. And in our paper, we also show that if we use the dense phrases as a document or passage retrieval component, we can achieve very competitive performance in a range of the NLP tasks. And we also took a closer look at the training paradigms of the DPR and dense phrases. We find that DPR learns passive supervision, and the dense phrases learns from the phrase supervision. And the DPR uses the BM25 to mine hard negatives, but dense phrases doesn't directly use any hard negatives. So that actually means that dense phrases actually use of other phrases in the same passage to actually act as hard negatives implicitly, which can be thought of as an advantage of dense phrases. Finally, we also made some great efforts to make the phrase index smaller. And we find that Fine-tuning the query encoder with optimized product quantization can return almost all the accuracy. We also propose to control the number of phrases per passage through phrase filtering. As a result, we find that if we only want to keep 8.8 phrases per passage, we only need 30 gigabytes storage with minimal accuracy loss, which already half the size of DPR and is also more accurate. So let me just conclude here. So in our DensePhrases project, we show that it's possible to achieve accuracy phrase retrieval at a billion scale. And the phrase retrieval naturally entails passage and document retrieval. And the phrase retrieval can be also made smaller and more efficient. Our code, models, and demo are available on this GitHub link. Thanks for listening, and have a nice day.